Hello and welcome to DAMSO, Domain Agnostic Score-Based Meta-Learning. I am John and I'll be presenting our paper to you today. So the solution of domain agnostic score-based meta-learning aims primarily to address the problem of cross-domain few-shot learning. So cross-domain few-shot learning was introduced 2 years ago by combining the problem of domain shift and few-shot learning methods. And in several papers, people have found that when there is sharp domain shift, the typical few-shot learning methods, such as prototypical networks or MAML, do not perform well. And this is critical to address because we understand that few-shot learning has the promise to help solve the reliance on large amounts of labeled samples. And we know that in practicality, domain shifts are very common. So if domain shifts do hinder few-shot learning, then that limits a lot of the good work that few-shot learning can actually provide. So what I'm presenting here today is an easy, intuitive way to combine transfer learning with few-shot learning so that we can deliver greater outperformance in the cross-domain few-shot learning context. So as I've emphasized, cross-domain few-shot learning is a very challenging problem, and it's a successful algorithm has to tackle both the sub-problems of transfer learning and few-shot learning itself. And so what we've realized from our research into this area was that a lot of previous meta-learning methods, they failed in the cross-domain few-shot learning context because they overfitted to the source domain and hence were unable to accurately transfer features across the domains. And on the other hand, for transfer learning, while they did perform markedly better than the meta learning methods, what they failed to do was to take into account the structure of the support set. So we understand that in the unique context of few-shot learning, what we have is both episodic training and episodic testing. So for instance, we have maybe 5 examples of each class, and we perhaps have 5 classes. That gives us 25 support samples. And at test time, we are actually trying to predict each sample. But if we simply just fine-tuned our model, as we do in transfer learning, on these 25 samples, what we lose is the information contained in the distribution of these samples, because we are in the fine-tuning process, we are merely treating these samples as independently and identically distributed. So we don't really capture the structure and the statistics of these samples. So what we do propose here is the idea of combining these two methods in a way that is intuitive and that can be used for many different techniques. So this is where score-based metric learning comes in. So in the first part, we utilize transfer learning to adapt the feature encoders to the new domain. This can be any form of transfer learning as long as it operates on the feature encoder. And then in the second step, we take these initial score predictions. So what the model initially predicts, for instance, whether this sample is a dog, is a cat, is a horse, and these scores then would then be post-processed for each of these 25 support samples and a query sample. And then they will be compared against each other. So this would deliver a more robust classification scheme that fully takes into account where this query sample is placed in the space of the support sample. So this allows us to fully exploit all information contained in the support set rather than throwing it away when we are just treating them as IID. So in terms of the data set and benchmarks, I'm sure that experienced readers would be familiar with the broad study of cross-domain few-shot learning, which was proposed last year. So in this, we have crop disease, Eurosec, ISIC, and ChestX and decreasing similarity to ImageNet, which is the source domain that we train on. And then this is our method is also tested on 4 additional data sets beyond this. DTD, which is the describable texture dataset, CIFAR, COP, and places. Right. Right. So now moving a bit more depth into our methodology. So we have a modified episodic training process. So what we do in the first step is that we have a process of fine tuning. And this is where we are just using a simple linear classifier after a feature encoder to produce fine tuned scores. And this is done by using cross entropy laws to both fine tune the linear classifier and our feature encoder. And note that only the last 2 layers would be fine tuned for the feature encoder. Right, so then in the second step, what we do is we have the score-based learning. So rather than just take the first step as it is, we further post-process the initial scores through a linear metric map and a graph neural network where the support labels actually come in. So this is information that we'll be fully exploiting. So then we'll have the we'll have a final score that's produced for all the query samples, and our backpropagation for the entire feature encoder would then backpropagate through the graph neural network all the way into the feature encoder. Right, so to have a more in-depth look at the score-based graph neural network, we have the figure below. And in this figure, what we do have is you can see how the support sample and the query sample are placed together, and then they are we have an adjacency operator followed by a graph convolution. And in our case, the graph neural network is 2 layers deep, so we have 2 steps of this graph neural network structure. Right, and then yes, we also do encode the support labels as a one-hot encoding, and we encode the query labels because they are uncertain as a uniform distribution. And so what this does is that it means that at both training and test time, we do fully see all our support samples simultaneously, and we do see how our model has performed on these support samples. So we are exploiting the labels that are in our support sample to propagate these labels towards our query samples. And now I'll briefly go over the results. So Damsel achieved 74.99 average accuracy on the BSCD FSL benchmark. This is markedly higher than both previous meta-learning methods, such as ProtoNet, and transfer learning methods, such as transductive fine-tuning. And this is also higher than the average accuracy attained by the best performing models from the challenge last year. And on the 4 other domains that we have added, the DTD, CIFAR, COP, and places, our model performs much better as well. So from the chart, we can also see that our model, the improvement delivered from our model is substantially greater from adding just data augmentation or adding more ensembles to the network. Right, so in conclusion, we proposed the novel idea of basing a metric learner on the fine-tuned score vectors rather than the feature vectors. This allows us to fully utilize the information contained in the structure of the support set while taking advantage of fine-tuning to overcome the domain shift. And as a result, we've achieved vastly improved accuracies. And what I would like to emphasize as a final note is that our solution not only decisively addresses the cross-domain few-shot learning problem, but it provides an outline for a new way of boosting classification models by further post-processing the scores by taking a support sample and labeling that, and then having that support sample guide our solution. Thank you.